Okay, so in the Larson and Edwards ninth edition calculus, this is the definition that they have for convergent or divergent series. So, for an infinite series, and we see we have a series which is the sum of the terms of a sequence, the nth partial sum is given by Sn, which is just the sum of the individual terms from the sequence. Now, if the sequence of partial sums, so we're talking about a different sequence now, we're talking about a sequence that contains these partial sums. If that sequence of partial sums converges to S, then the series will also converge, and the limit S is called the sum of the series. All right, so remember, for a sequence to converge, that sequence, the terms of that sequence have to have a limit, and that limit is going to be called the sum of the series for these sequences of partial sums. All right, now if the sequence of partial sums Sn diverges, then the series also diverges. So let's take a look at a few examples of what we're talking about here. All right, so for instance, let's take a look at this series. Look at this series that starts at 1, from n equals 1, and goes to infinity, of 1 over 3 to the nth power. All right, so let's take a look at this series. Now, in order to determine the divergence or convergence of this series, what I have to do is I have to look at the sequence of partial sums. So first, let me see, first partial sum, the first partial sum would be 1 over 3 to the first power, n would be 1, so that would be 1/3. That's actually also the first term of the sequence, an, which form the terms of this series. So then the second term of the sequence of partial sums would be S2. It would be the sum of the first term of the sequence and the second term of the sequence, which would be 1 over 3 to the second power, 1/9. And this sum would be, let's see, this sum would be 4/9. And that would be the second term in the sequence of partial sums. So what we have here is we have two things going on. We have one sequence where an, that sequence, is a sequence whose terms form the terms of this series. And that sequence is 1 over 3 to the nth power. So when n is 1, you have this term. When n is 2, you have 1/9, which would be the second term of this sequence. And when n is 3, you'd have 1/27, which would be the third term of this sequence. But you also have the sequence of partial sums, which is going to be called Sn. And Sn is going to have a form. The first term in Sn is 1/3. The second term in Sn is 4/9. Let's see what the third term would be and see if we can get a general pattern here. So the third term, S3, the third term would be the 1/3 plus the 1/9 plus 1/27. So you see, each term in this series, which is the sum of the terms of this sequence, each of those terms is one of these numbers, either A1, A2, A3. See, the third term here is A3. The third term is A3. When I add these up, what I'm creating is a series. And when I take a look at the partial sums of that series, it forms a sequence. S3 would be the third term in that sequence, and S3 in this case, let's see, S3 would be 13 over 27. 13 over 27. So the third term in the sequence of partial sums would be 13 over 27. And let's calculate another one. Let's calculate a couple more actually to see if we can develop a pattern. That would be S3. That would mean S4 would be 1/3 plus 1/9 plus 1/27 plus 1 over 81, which would be 3 to the fourth power. And this sum gives us 40 over 81. I'm beginning to see a kind of pattern here. It seems as though um, the number on the bottom and the number on the top are related in a way that if you take the number on the bottom and divide it by 2, you get exactly zero point 0.5 more than the number on top. For instance, 9 divided by 2 is 4.5, which is exactly zero point 0.5 more than 4. 27 divided by 2 is 13.5, which is exactly zero point 0.5 more than 13, and so forth. 81 over 2 is 81 over 2 is 40.5, which is exactly zero point 0.5 more than that. Let's see if it works for the next one. S5, the fifth partial sum would be 1/3 plus 1/9 plus 1/27 plus 1 over 81 plus 1 over 243. So this seems to be uh, 121 over 243. 121 over 243. It works again. So let's see. Let me see if I can figure out a way of describing that. So let's see. So I'm going to infer that the nth term in this thing is going to equal, well, the denominators are just 3 to the nth power. 3 to the nth power. But once you've determined what the denominator is, the numerator is going to be the denominator minus zero point 0.5. So the numerator is going to be whatever the denominator is, 3 to the, actually it's not even the denominator, it's half of the denominator. Half of the denominator minus zero point 0.5. So let's erase that. All right. So the numerator, once again, like I showed up here, is going to be half of the denominator. Half of the denominator is 3 to the nth power over 2. Half of the denominator minus zero point 0.5, which is 1/2. So it seems to me as though this turns out to be 3 to the n minus 1 over 2 times 3 to the n. Ah, so there's a closed form for this. This is the nth term of this sequence. So the sequence of partial sums, the sequence of partial sums, Sn, the sequence of partial sums seems to be this sequence. 3n minus 1 over 2 times 3 to the n. All right, this seems to be a description of the sequence of partial sums. Now, the definition over here says for an infinite series, so for the infinite series, let's recall what the infinite series is. The infinite series is this one over here. It was 1 over 3 to the n, and I think n is going from 1 to infinity. So here's the infinite series that I'm talking about. So in this definition on the right here, for the infinite series, the sum from n equals 1 to infinity a to the n, the nth partial sum is given by Sn. So I found Sn right here for this series. That's the sequence of partial sums. And it says if this sequence of partial sums converges to S, then the series converges. And S is called the sum of the series. So if I can find out if this converges, this sequence right here, I will have proven that this converges by the definition of convergence. So let's go ahead and see if we can find the convergence of this sequence of partial sums. So I'm going to take the limit as n approaches infinity of this sequence of partial sums which in this case is the limit as n approaches infinity of 3 to the n minus 1 over 2 times 3 to the n power. And by L'Hopital's rule, we see that this limit is equal to, I believe, 1, actually, yeah, 1/2. So, there we found out that not only does this sequence, or not only does this series converge, this series right here, but it converges, and the sum of this series is 1/2. All right, so there you have it.